Okay, I'll just call it. Okay, I guess we're ready to go. Good evening. Welcome to the July meeting of the Santa Barbara Astronomical Unit for July. I'm Jerry Wilson, I'm the president. I wasn't there the day they voted on officers. The SBAU is supported by the Museum of Natural History in a wonderful and collaborative partnership. And I want to welcome Randy Rouse and the CEO Mayor of Santa Barbara, and Luke Swetland, the CEO of our museum here. Our other officers include here tonight is Ronnie Herron, an ex-radio announcer, used to be known as the Baron Ron Herron, but he's joined our club as the vice president. Also Pat McPartland, treasurer and works manager. She's out recovering from a medical situation, doing very well, I hear. Tessa Flanagan, our secretary, and other enthusiastic supporters of our efforts here. Okay. Oh yes, and we have a thing. We're going to take a few minutes at the beginning of our meetings, this one, to have a little, do a little of our business. So it's going to be very short and it's going to be very sweet because a lot of our officers are some of our key players, like the merch manager, is out, so we won't have the advertisement of our merchandise that's available. But if you see anything that any of the club members are wearing and you want one, let us know. So our guest speaker tonight is a kid I met back about 1995 when he was about 8, I'm guessing, and very enthusiastic, very bright, very inquisitive. And the major thing I noticed about him from the beginning is that he has the knack. Now, if you follow the Dilbert comic strips, you know that the knack is the basic requirement for being a scientist or an engineer. And it means that you have a natural and native understanding of how things work, or curiosity about it. So he definitely had that. I attended his graduation from Cal Berkeley for his bachelor's degree in mechanical engineering. And also, I wasn't there, but he graduated with his PhD in mechanical engineering from Georgia Tech. And then he got a dream job for an amateur astronomer, is piloting the telescope, the helicopter on Mars. So, lucky guy. Just remember, we go way back. Okay. So Ron will give you the official introduction for that. My iPad just went blank, so we're going to wing it. Our administrative stuff for today will consist only of Chuck McPartland going over briefly our outreach for the month of July. And he'll be up here in a second or two. Is he still in the Observer Planetarium? Oh, here he is, okay. Now, the guy that was up here and keeps things running for us is Tom Totten, our webmaster, and also our telescope inventory, equipment wrangler. Okay, Chuck.
Okay, thanks, Jerry. I'll keep it quick because we want to get to our speaker. We have regular star parties here at the museum on the third Friday of every month, usually. Free. The telescope set up to look at cool stuff in the sky, and there's lots of that in the summertime. We also also do third Friday of every month at Westmont College, their observatory. And we do first Tuesday of the month at Camino Real Marketplace, which is Telescope Tuesday. We mainly look at the moon because there's a lot of light there. And then we're also doing Refugio State Beach and Carpinteria State Beach and Kachuma Lake during the summer. There's piles of propaganda here in these dispensers, stuff about astronomy in general, and also stuff about the club and our activities, especially bookmarks or a quick reference. They have our URL on it, SBAU.org, and you can go there and find out all about what's going on. Thank you.
Thank you, Chuck. And now our Vice President will come up and introduce tonight's speaker.
Thank you for dressing up tonight, Jerry. You look great. You look cool. Thanks.
Thank you, Mr. President. Godfather. Make you feel like that. Huge.
Okay, everybody. Whoa. Good sound system tonight. I gotta make it quick because they want me to get into things, but I got stuff I do at these events. And I don't think anybody objects. I'm up here to represent SBT, a very fun club, a very long time club. We're at the end of 70 years of astronomy clubs in Wisconsin. The first one started in '55 back at City College. And now we're known as the Santa Barbara Astronomical Unit. And just to show you guys what a great club it is, you want to make some new friends. I can't think of a better one than this one. I'm rubbing elbows with people with PhDs, and not one of them wants me to call them doctor. And why is it the fun club? It's because it's the fun science. I mean, if you were geology, you have a big pile of stuff up here maybe to look at and burn our fingers through. Paleontology, what do they discover a dinosaur every year or two? Anyway, let me get my notes. Because one of the things I do for this club that I'm very proud of, I want to mention quickly before I take my show of hands and then bring Martin Cacan on, is I get to host a vlog. We have a weekly podcast, which I understand is not the same as video. Podcast means you hear it, but some people can hear it, live you can hear it. It's on YouTube, and it's been on there over 4 years. We've rarely missed a program. It's Monday mornings from 11 to noon. You're all invited to tune in to the SBAU Astro Hour. I think it comes up on one of these shots from time to time. And we're there 11 to 12, where there's 6 of us on the screen. We start the show every week with silly science cartoons that are forwarded by the president. And I want to introduce, on Saturday's meeting, our planning meeting, I want to introduce maybe do a little recap every month. In any event, let me get some sound going here. Take my glasses. I want to do my show of hands real quick before we bring on Martin. How many of you, raise your hand if this is your first time ever, you're a newcomer to this event? You just heard about it. Keep them up, because we got to make a good impression on you guys. Okay, we've seen you. Raise your hand if you've been here before, but you're not a member of the club. Okay, thank you. We did something right. Oh, Martin's mom, Lynn, is here. Okay, raise your hand just out of curiosity if you're a member of the Museum of Natural History. Oh my God. Okay. How many of you saw the ad or the mention in today's Independent? You're here because of that, a few of you. All right, now for the members of the SBAU. All right. Now keep your hands up if you want. Turn and do a high five with another member if you want. Got my permission. What else did I want to say? I want to call attention to a couple. Raise your hand if you happen to be, raise both hands if you're a mayor of this city. I'm running for re-election unopposed. Jerry and I. Raise your hand if you happen to be the head of the astronomy department up at City College. Are you here, Sean Kelly? Okay, no hands, so he's not here. How about raising your hand if you're a member of the club and you've written not 1 or 2 or 3, but 5 articles for Astronomy Magazine? Raise your hand, Dave Grossman. He's in the back. And he will be one of our speakers in December. We have in-house speakers on the stage. We meet down in the smaller little room that I like better than here, actually. It's okay. This is like the gymnasium at the school. That down there is like the professor's forum. Anyway, let me tell you who's coming to town to talk to us in the next few months. And I'll bring on Martin Cacan. A month from today, or actually a little less than that, it'll be August 1st or 2nd. August 2nd, Dr. Stephen Kane from UC Riverside is going to take us planet by planet, I guess around the solar system and maybe exoplanets. He's an expert on Venus. He's going to check out habitability. I knew I was going to. The habitability of planets, the possibilities of life on them. Could there be life? Including, I guess, Mars and maybe some moons. September the 5th, we have a UCSB grad student by the name of Ish Kaul, very nice young man from India, on his way to getting his PhD. And his talk is, I have no idea what he's talking about, galactic atmospheres and rain. That's what he calls it. We've got somebody probably pretty good I'm working on for October 3rd. I wish I could tell you who it is. It looks good. I'll tell the club meeting on Saturday afternoon at 4 who maybe October 3rd speak what? October? How did you get that? You have to verify.
Well, you told me so.
Here's the deal with Alex Solopenko. You told, well, that's right, I told you on the phone, and you said you thought he graduated at Santa Barbara High School.
No, that's Pueblo.
He's a DB grad just like our guest tonight. Okay, well, then forget that surprise. Believe me, he is renowned, world renowned. He's probably not up there in the stratosphere with Brian Cox and Neil deGrasse Tyson, but I see him on half the videos that I'm watching on YouTube. Okay, so maybe we'll have him. He's supposed to be attending his 50th class reunion the day after, Saturday, October 4th. He said he'd get back to me and let me know if they're not doing something special for the Friday, which would keep him from coming here. But if he graduated at Santa Barbara High, we could have him in town for that weekend.
That's Pueblo.
What?
Graduated from TP, Del Pueblo.
Did he really? I suppose it was before Katy Perry that wanted it. It was 2 years before Katy Perry graduated. In November, we have another Class A guy from Caltech named Dr. Phil Kornbutt. And he's at Caltech, and he's going to be speaking about the NASA Sphere X program, which he's involved with. We got him through Tessa, our secretary, who told me that he was speaking to a fundraiser event for the Mount Wilson Observatory, and I checked. I said, "Oh, I'll look you up." They were charging $50 to get in. And I said, "We can't afford this guy." And she said, "Try him anyway. He may be doing him a favor." So I called him back, and he jumped on it. "Yeah, I'd love to come do it. I was just at your museum with my daughter, checking out the mammoths on Santa Rosa Island exhibit." So he's going to be here on November 7th. And then we'll have our in-house in December with two of our guests, David Grossman, and David's going to be talking about sonification, sounds in space, the stuff that he wrote about in Astronomy Magazine, which is the Bible of this industry. And the Tessa gives us an update on dark energy. That's two half-hour programs in one night, and we'll be down below at Farron Hall. So, with that in mind, please join. We'd love to have you in. We could use a secretary. If you have secretarial experience, come 2026. You'll meet a lot of new friends. And we might even need a new treasurer, somebody that's good with numbers. So let's do it. Martin, on your way up, come on up and I'll read about you as you come to the stage. A native, now guidance and control engineer for JPL. Martin Cacan was the chief pilot of the Ingenuity helicopter, which we have on stage, a replica. He'll tell you about it. Assisting in over 50 flights through the Martian atmosphere, Martin specializes in modeling dynamic systems and state estimation, whatever that is, contributing to NASA's missions like Psyche, NISAR and ISAR, and another Mars chopper. You're going to have to tell us about that, my friend. And he's also UC Berkeley grad, right? Sure. Okay, Martin Cacan.
I need to go on dual technical switch.
No.
Are we all good?
Yeah.
All right. So welcome. I said I'm super happy to be home, back in my hometown. See a lot of family, friendly faces here. So appreciate it all. A little bit of background on myself. I joined the Ingenuity mission when we already had landed. So I was not there as part of the development, but joined as one of the pilots for Flight 14 and became chief pilot at Flight 38 and took us all the way to Flight 72. Yeah, we good? Sorry, one moment. All right, hopefully we got that all squared away. So anyways, this is going to be, pretty low-key lecture, a lot of photos, trying not to get it too technical. Be prepared, there's one technical slide. All right, a little bit of background. Living on Mars is hard, all right? The rover, it's a challenge for the rover, but the rover has a lot of advantages over us. The rover gets a nuclear battery that provides power and heat. Heat's pretty critical. It has an antenna that's powerful enough to communicate to orbit with our communication relays that bring the signal back to Earth. Ingenuity here, which I have a full-scale model, so this thing, width is about 4 feet up here. People can come take a photo at the end. Please just don't touch. I had to check this out from work. It's like on my dime if you're a kid. But as you can see here from the photo, and up front we have an antenna that generates all of our power. We have this small box that's insulated here, and that's where we have all of our batteries and our flight electronics. These batteries you probably find in the cordless drill in your garage. Most of these sensors and camera parts all came from Pixel, old Galaxy, just a lot of commercial off-the-shelf parts. And most importantly, we spend a lot of our battery life running resistance heaters trying to stay warm on the surface of Mars. Mars is cold. And so one of the engineers on the project used to joke and said that Ingenuity was just a portable heater that flew sometimes. And it's true. Thermal ate about 75% of our power budget, and about 25% was left to fly. All right, just one little video here just shows, kind of where we came from, right? There were a lot of people that didn't think this was necessarily possible, right? But we had a couple brilliant minds and a director who wanted to see this happen. And this was the first time that we proved that, it was going to be possible, right? This is far from a successful, completely successful test, right? You see we are going to crash here in a minute. But we proved this possible. We proved that we can generate enough lift in this really small Martian environment, to actually fly. And so going from that, super early proof of concept, we then here in the same chamber were able to test a much more flight-like vehicle and really prove to ourselves that we think this was going to work. And for anyone who knows anything about helicopter stability and control, it's difficult. And, we had to completely redrive all the equations here to make it work in, 1% of Earth's atmosphere.
So Martin, was that a vacuum there?
Yeah, so this is our 25-foot vacuum chamber at JPL. They basically pump this down to almost a near vacuum, and they actually backfill it with nitrogen to get up to Martian environment. So make it as realistic as possible, right? Not just the equivalent air density, right? They actually try and make it more Martian atmosphere-like. In the first video, it was super lightweight, and that's how we kind of accounted for the mass difference. In this video, you can't quite tell, but there's a tether going up to mass unloads it to try and make it more equivalent, since we have three times more gravity here. All right, so stepping back, we proved that we could fly. We got sent to Mars, and here's just a nice, I think, outline of our entire mission. Right, so we originally were put down to do 5 missions. We did that successfully, and NASA was like, great, keep going. And we quickly found ourselves without the tools, without the processes, without the plans in place to do all of this. And so there was a lot of development along the way, and constantly we're faced by new challenges. This first half of the mission was a challenge. We learned a lot, but this second half of the mission was, a scale of magnitude more difficult going up this delta region called Shonen. You see, again, 72 flights in total, almost 10.5 miles that we traversed. Records broken, consistently as we kept pushing the boundaries of everything we could do. But as all good things happen, they come to an end. And I'll talk a little bit more about that. So, looking back again, 10.5 miles, landed here in the bottom right. We originally thought, Santa was this really difficult challenge for us to get through, but that really was the training grounds for the delta that we had to go through. So you can see, right, this is basically a view of Jezero crater. The crater rim is off to the left, but again, very much, you see why we call this a delta. This looks like it used to be a river delta. It's believed that Jezero crater was twice a lake. And so, there's a lot of stories to tell from across all of this, which, made it very difficult to try and make this a reasonably length talk. But I wanted to start with, first, trying to give you an idea of how we actually do this. How did we manage to fly 10.5 miles on the surface of Mars? Well, not like we do on Earth, right? The max flight time of Ingenuity was about 2.5 minutes. At best, it takes 6 minutes for a radio signal traveling at the speed of light to travel to Mars and back. It can go up to like 18 minutes. So, we're not joysticking this thing from the ground, right? I think you gotta think Ingenuity as a helicopter is a little bit more like your Tesla, right? We put a lot of smarts into it so that it can drive itself. You get a lot of tuning and a lot of selection you can have for parameters, but basically as the pilot, you tune the software, you pick what you need, all the parameters on a flight-by-flight basis. And so just to give you an insight, prepare yourself, here's our one slide of technical content. This is just a glance at how we do our autonomy on board, right? So again, I'm sure a lot of people are more familiar with Tesla Autopilot. It looks for other cars, looks for other things, tries to scan. We do something very similar, right? And so I'm going to play this video here in a moment. But basically what we do is we try and track features so that, usually rocks or various things on the surface of Mars, and we look to see how they move, right? And that gives us information about us and how we're moving, right? So it's a really simple example. You're driving down the road, you're looking out the window, and you see a bunch of trees going by, right? You kind of have information about that. The trees are not moving, you're moving. And so that's the whole kind of concept, right? So if you fuse that with some other sensors, you get this. So, all right, I have a warning here. There is some strobing and flickering going on. And you're going to have to kind of bear with me here. We get our data down a lot faster than we get our images. So the images in the background are updating much less frequently, as you see, than all the dots moving around. But all the dots moving around, these are the features that we're seeing on the surface of Mars. And in particular, what we care about is how they move over time, right? We basically see, it incrementally moves step by step by step. And we can see, that we are moving. So in this little flight diagram here, we're starting here in the bottom right. We're flying up this hilltop and working our way back down. So don't really pay attention to different colors of the green and red. You can mostly see just how they're moving. You see here, there's this kind of like white streak of the rock. That's the white streak we're seeing right here. And then these blue boxes are basically where Ingenuity is saying, if I had to land right now, where's the safest place for me to go? And so this was a really important flight software update that we put on the vehicle about halfway through the mission. And that allowed it to self-determine where to land. So it would kind of get to its end target, and it would look, and it would sit here and be like, okay, where's the best place? And once it latches onto one, it grabs that and holds onto it. And so in this case, we, picked a target right very clear where we have here, and we come down and land, right? We actually see that here's our previous footprint, so we actually came almost exactly back to where we started, which was really cool in this case. All right, but ultimately, right, it's a massive team endeavor to try and fly a helicopter on Mars. As a pilot, I like to think of myself kind of in the hot seat, in the thick of things. But there's a lot of people we have to coordinate with. So this kind of gives you a brief rundown. At the top is science, right? We are there to explore Mars. We are there to study geology, and anything else that we can learn. So ultimately, we are there at the request of the scientists and trying to help them in any way. So if there's points of interest they're curious about, they'll try and let us know. So in this example, where we have the star, they were kind of curious about this rock unit. So we flew over it, grabbed this great photo, sent it back. As I'm not a scientist, I can't exactly tell you all the nuances of this, right? But a lot of the, interest from the science team was to understand, is this a place that we want to go, and we want to sample, and we want to bring our, much more expensive rover in and look at this more closely? Or is this maybe part of the same rock feature that's, over yonder where the rover already is, and they're trying to, piece together the bigger kind of geological team? Really importantly, we work with the scientists as well, though, to find safe places to land. Mars is full of rocks, and that is not great. You can imagine trying to land on a large rock we're going to tip over. And most importantly as well, we get atmosphere and weather predicts from them. So based on the density that day, given the temperature and whatnot, that's how we set our rotors. We also work very close with the rover team, right? This is the main mission, and we're kind of just a secondary unit to them. But they're also very much driven by science. They provide us usually these strategic routes. So as an example, this blue line, and that's basically like, hey, we're going to go this way. So that's roughly the plan. We then work again with the scientists to try and find safe landing regions along that way, which you could say are these kind of yellow airfields. And again, kind of work with the rover team to also provide any scouting if there's like a difficult patch for them to drive ahead in the future. Can we get there first, try and take advantage of it and help them out. Telecom, right? So as I mentioned, the antenna on Ingenuity only communicates back to the rover. And so it's really, really, really important that we stay close to the rover. And so we use the telecom team, our onboard antenna, basically, bit about like line sight communication. So it was really important for us to stay ahead, because if we ever fell behind, there's a chance that we wouldn't ever be able to communicate with the rover again, and we'd have a mission end. And so you see in this example, at the start of the flight, we were this green dot by Mount Julian here. And the rover is the teal dot up here in Echo Creek. And if we flew to the star, we see that we would not have communication with the rover. However, as long as we have communication with the start, we can get the sequences, and we can command the vehicle, and it can fly. If the rover ever got too far away from us, right, we would never be able to get the sequences to take off to then fly within range. So it's really important that we follow the rover from the front. So that ended up being a difficulty on its own, when you're trying to stay ahead of this vehicle that has about 200 backseat drivers, and everyone's like, let's get gas, but I need snacks, It's a bit of a wild ride. Too many names, so I'm just going to jump all in here at the end. Power and thermal team, right? So what time of day are we going to fly? How long are we going to fly? You know, in winter we were very power limited, and in summer we were very thermally limited. We also had to work, you know, constantly with the operations team. You know, we flew about once a week, but we interacted and operated the helicopter daily, right? We had to stay warm, right? You had to set alarms to communicate. There's a lot of things that need to happen on a day-to-day sequence. That team, you know, basically took care of the bird for us. And of course, you have to do peace management, right? They basically gave us final approval on everything, you know, helped us form our strategic goals and overlap those with the rover, and overall did a lot of coordination too. So now that you've gone and you've talked to all these people, and you know, there's been some arm twisting as we've all tried to, you know, get everything that we want, how do we plan a flight? So basically, it starts here in the top left. It's a lot of planning, right? It's kind of trying to determine, you know, where we want to go, trying to set waypoints, set velocities between these waypoints, trying to determine, you know, what we want to try and take pictures of, how can we like maximize our goals. And so the goal in this flight was to try and get as far north as possible of this, you know, kind of left side. And also we wanted to take a picture here to the west, right? This is basically a time mission when we were leaving the Delta region and entering the foothills. And, you know, we really hadn't seen what this ground was like before. And so it takes a lot of iteration, which is, you know, not shown here, to kind of go and test. We run a lot of simulations to kind of see how the helicopter performs on that flight and make sure everything looks safe. Basically what happens over time is, you know, we have knowledge error in our position. So, you know, imagine you're trying to drive down a straight road, but you close your eyes. You know, and so, you know, after 100 feet, you know, how close do you think you are to the middle of the road? You know, kind of the same for Ingenuity, right? Its eyes are open, but it still accumulates some error. And so when it gets to the end, it actually doesn't quite know where it is. And so we have to tell that we're getting here though. So, yeah, so we kind of iterate through this whole cycle, get something safe, we uplink it. It's about a 24-hour wait for the signal to bounce between all these, you know, up to the orbiter, down to the rover, from the rover over the helicopter, and then send all the data back down and around. So flight balance, though, are by far the most exciting thing. I'm sure people have seen photos of, you know, back in the 50s when they're, you know, downloading, you know, photos from the moon and stuff like that. And it's literally the same, you know, just loads a lot faster. But, you know, we're all like glued, and you're really seeing the you know, the most recent image from Mars. It's really quite amazing. So as part of this downlink, you know, I'll do a lot of flight health assessment. One of the key elements is localization. Again, kind of have error growth in where we think we are. And so at the end of the flight, we download, this is the descent as we go down to land. And we look at these and we say like, oh, well, you know, this rock is that rock, and this rock is that rock, and you look at a satellite image, and you can much more precisely say where we are at the end of the flight. We use that information into our plan to plan the next flight. If we're really lucky, we landed near where we attempted to land, and that means that our next plan is probably a good one because, you know, our starting location that we were hoping to have and what we actually have are close, and so on we go. There were situations where we missed, you know, we missed pretty good, and we had to add a whole extra flight to make up for that, or, you know, kind of change the plan. And so, you know, there's a lot of churn that happens in those type of moments. All right, so, but again, all that hard work, and there you are at downlink, and here we are seeing the foothills here for the first time. This marginal unit is what the geologists call it. So you have the crater rim in the background. We have kind of these foothills here. And you can see, you know, in the foreground, great place to land. A little bit further away, makes me pretty nervous. But, you know, it was great to see, and this is, you know, the type of advantages we got by having a little scout on Mars. So, you know, you really can see that it takes, you know, hours of preparation to get the perfect shot. This was, you know, the flight plan here in the corner, all these like staggered waypoints, all of these images we tried to capture here. We have Belgian crater in the background. This was the best we could do at capturing a selfie with the rover. You know, the rover did a selfie with us. I showed you guys at the beginning, but you know, we have our shadow down here in the bottom. We have the rover, again, Belva crater in the background. I think this shot's really cool because you also get the rover tracks coming across the scene. There's actually some funny stories in that as well. So I don't know if you guys know what a Martian traffic jam looks like, but this is the sign of one. So basically what happens with the rover is something very similar with Ingenuity, like I mentioned, is that over the course of the drive, its certainty in where it is kind of degrades, right? It's kind of more uncertain of where it is. And so it has a really important rule though that says, "Thou shalt not drive over the helicopter." And so the way that they do that is they put this 10-meter keep-out zone, let's say, around the helicopter. So when the rover is driving autonomously, it stays away from this region. Well, what happens is as the rover's position uncertainty grows, it has, doesn't know where it is. Let's say it has 10 meters of position uncertainty. Well, now you need to have that keep-out zone be the 10 meters that you know you need to keep, plus like the 10 meters that you don't know where you are. So now you need to be 20 meters away from this thing. And so basically what happened is the rover approached us at the end of its drive. We had at this point a huge keep-out zone around the Ingenuity helicopter, and it basically got shoved into the corner of its allowable drive zone and got stuck. And so that's what you kind of see. This is it kind of coming up this way. It tried to go around us. We're the star. Again, we're not even close, but it doesn't know, right? Better safe than sorry. But then, the next day, it knows where it is again. The keep-out zone on the helicopter shrinks. It scoots right on past us. No big deal. Next is this position here. You kind of see where the rover pulled out to study one of these rocks here in Echo Creek. This is originally where we were hoping the rover was going to be when we commanded this flight. However, we kind of got moved to Seoul just due to the schedules with the rover. By the time we got the photo, it was off there on the left, but still one of my favorite memories from the entire mission. So, having the camera on the helicopter on Mars, again, really provided new advantages, right? Seeing things from the air really provides a new capability, being able to traverse into areas that the rover would never go. And so this was one of those examples. We were basically flying past this hardware and decided to do a divert to basically take these pictures of the entry, set, and landing back shell, right? So this is the top half of this vehicle that basically brought the rover and Ingenuity to the surface of Mars. And the coolest thing about this is 2 months after we took these photos, there was a talk at JPL where the mechanical engineering team who designed this literally were doing the impact analysis and saying, it looks like that's a little over-engineered, and this crumpled differently than we thought. And the fact that they got a real-world test case of the thing that they built, was just so exciting. But overall, we were there for science, right? So it's a lot of time scouting rocks, looking at rocks. I love some rocks, so I'm all for it. But it was a lot of fun when we found a lot of things you often weren't expecting. Right, I think Mars is full of the unexpected. And so in this case, we went to try and study this outcrop to the west here at Willow Park. That was kind of the science interest at the time. And then we just so happened to land in this space short of it after we went and scouted. And we always take a photo when we land on the ground. And we got this photo down, and we immediately got a phone call from Ken Farley, the chief of the Mars 2020 rover. We had found this vesicular rock, which I had to Google, but it basically is a type of volcanic rock. Basically what you see here is all these little great nodules. You can see, the type of volcanic rock having all little gas pockets. You get a little porous rock. But again, you see what the planned path of the rover was, this blue line. And after discovering this, the rover diverted its actual path is this gray line. And basically identified that this was previously a lava flow that came into the lake.
Martin, what kind of distance is that from the blue line to Dream Lake?
That's probably about 400 to 500 meters. Sorry, I do everything engineering-wise in meters here. Okay, sorry, yeah, there's a lot of videos on the slide, I guess. All right, so one of the really cool things is that the longer you spend on Mars, the more time the scientists have to come pester you. They're like, hey, what if we did this? And so, you know, one of the things we often try to do is get video of the helicopter from the rover. And in this case, we really were curious about how the dust gets kicked up by Ingenuity taking off, right? How does dust move on Mars? How's the atmosphere? You know, there's just a lot of uncertainty in a lot of the atmospheric models, a lot of the ground effects. And so this is a, you know, clearly post-process video where they tried to highlight all the differences from one video to the next, and that really accentuates the dust. What you don't really see here in the top right, this is supposed to be a little animation. There was a point for 3 weeks during Mars conjunctions, basically a period of time where Mars is on the opposite side of the sun from Earth, so we can't send any radio signals to or from Mars because the sun is a gigantic radio emitter. And so we just parked ourselves in a little sand lot for a couple weeks and purposely did this little flight so that we could get this. This is one of our footprints from the previous flights. We could get it into our field of view. And multiple times a day we took photos, and what you're not seeing are very minute shifts in all these little pebbles. Basically, again, there was a lot of interest from the scientists about, you know, how does sand move along the surface? You know, what are the mechanisms? Aeolian motion. All right, that's I had to go out to. You know, and then there was a great opportunity. You know, throughout the course of the mission, you know, we constantly needed to try and fly faster, fly higher. You know, we always needed to go further. You know, we were a tech demo. You know, we were this thing that's like, you know, if anyone's gonna take risks, we're gonna take the risk, right? And so, you know, we constantly tried to just do a little more every single flight. And one of those flights, we wanted to go up to a new record altitude of 24 meters. And that's what we do here. This is the video from the rover, and this is the nav cam that looks straight down. And so in this case, instead of just flying up to 24 meters and flying back down, the scientists came to us and they're like, hey, what if we hover at all these different altitudes? We can basically have this windsock, and we can basically try and see if we can understand the wind at different altitude layers above the surface. Because we have put wind sensors on Mars, but they've all been attached to the rover or landers, stuff like that, they've all stayed very low. So this is the first time we really were able to do, you know, above ground atmospheric sensing. You know, and one of the byproducts of all of this is that we collect all the data that we take, and so we map the Martian surface as we go along. And so this is just a stitch together of all those nav cams all together, and it provides better resolution than what we get by satellite. So it can often be useful for the rover team if they were to come traverse through this area to get just a little better detailed resolution on what's ahead. So this was us basically a photo, I think, from our first or second flight. We were designed to fly in this, you know, flat airfield. The rover drove around. The scientists, you know, even us engineers on the helicopter looked out and were like, all right, this is where we're going to do it. This location, it doesn't quite look it, but it's very flat. All these rocks are mostly flush with the surface, so there's a lot of features to look at in our camera, but nothing really all too concerning to land on top of. The cool thing about this is that this is the Jezero Airport, JZRO. This is an officially designated airport, just like LAX or SBA. So hopefully one day we will all be able to go to Jezero. But again, as the mission progressed, this is us going into the Santa region you saw on the map before. You know, we're no longer in a gigantic parking lot where we can go wherever we want. We now were traversing between, these large rocks and, trying to find safe places to land in the midst of it. And it only got harder. Anyone feel optimistic? Has anyone found Ingenuity yet in this photo? I'll let some people stare for another 2 seconds before I spoil it here. We are down in the bottom left corner by this big rock. So the perspective on this, I will admit, makes this look a little bit more daunting than it is. There is a safe space to land there. There's a bit of a sandy patch. But this is what we started to have to deal with. And over the course of the mission, we uploaded 9 software patches to keep pushing what we could do to expand our capabilities. And being able to traverse this type of terrain was all dependent on that. So another way to kind of highlight that is here we are on Three Forks. The foreground of this image, this is the type of ground we've been flying on for ages. This is the basically very close to the terrain where I showed you the vision navigation. All works very well. We're used to flying these big flat areas. And all of a sudden, we had to fly up this delta region, this feature that was way on the horizon. All these features that had always been on the horizon was now that hill we had to climb. So here's the photo of us going right up over that. And, when we had to do that, it was, very monumental. So, again, there's a lot of parts of our journey that I could try and highlight. I'm going to talk here just a little bit about kind of the period transition at the end of the mission when we're kind of coming out of the Delta region here into the marginal unit. Again, the path here was really challenging. We see the blue lines are all the various options that the rover was considering. And basically trying to travel south, there was no real good airfields. There's an airfield here, you see kind of these sand ripples. Sand covers the rocks, right? So generally speaking, sand is a good thing for us. You don't really see any until you get over here, down here, and we couldn't get that far. And so it was, unviable for us to go that way. And so we went up here through the river valley of Alice. And so again, kind of finding the path through, making it all happen was definitely a difficulty, but constantly found new opportunities to again, push the limits of what we did. That record altitude flight that I showed you happened right here. We then used that confidence to fly higher to fly faster, and so in our next flights we set multiple speed records. We had this really awesome opportunity to do a solar ray cleaning event. So this goes back to conjunction, when I mentioned, right, where we basically sat in this little area for several weeks. It's a little bit hard to tell in this photo, but this sand pit is ever so slightly darker than the rest of the Martian region. And basically, one of the things that I learned as an engineer is that Martian dust is red, but a lot of the Martian rock and regolith, kind of dirt, is black. And it's much more darker in color. And so when you see from satellite imagery darker regions, it means that something is coming through, disturbing the dust. Right? And so what this means in this case is that wind is coming down this channel and it's displacing the sand. Right? And so we purposely parked just downstream of one of these sand ripples. And the whole idea is that this was just an extremely mild, sand degrader. What's the word I'm looking for? Or a water jet, but for sand. Or I'm talking about. Oh my gosh. Okay, but this is like the same time when we were doing that, the Aeolian study of the sand motion, right? So while we were both trying to get science out of trying to understand how this, the wind moves the sand particles and all this, we were using that, from an engineering perspective to try and clean our arrays. Sand blasting, okay, very mild sand blasting, if you want to think about that, right? And help us clean our arrays. And one of the most fun things that I had the opportunity to work on was this in-flight system identification campaign. There were a lot of firsts on Mars. We had our first flight. This was our first in-flight system identification. So basically, the whole goal was to try and better understand how the vehicle flew. That allows us to basically make the next helicopter all that much more successful. So this was a really amazing engineering feat that required us to fly at 10 meters per second for airspeed, about 22 miles per hour. And that also was kind of driving a lot of our goals to set these new speed records so that we would have the confidence to get to this point in the mission and say, yes, we can fly at 10 meters per second. We've done it before, and execute that flight. So, the goal at this point was to try and get up to Bright Angel and meet up with the rover. We were going to try and do a 3-year anniversary selfie again. Alas, not all things happen the way you want. And so here in Flight 70, you kind of see this photo from the end of the flight. But I'll kind of call your attention to this video here in the bottom right. So you see, this is the nav cam. We see here at the beginning, there's a lot of rocks between all of these sand ripples. And basically, as we start flying further west, we just see, fewer rocks between the ripples. We just see more and more bland sand. And so, again, while sand really protects us from rocks, it kind of hides some of the features that we need to see. And so, sadly, Flight 70 was our last fully successful flight, and both Flight 71 and 72 basically had errors because it could not track features in this super bland terrain. It was basically on this path up towards Bright Angel. So, after Flight 72, we came down, and the first photo we had down showed this shadow of our rotor, and we sheared the tip off. It was kind of unclear to us how bad the damage was, but a couple of days later, the rover was able to catch up and grab a photo. We found not only was one of the rotors that we saw in the photo damaged, one of the rotors had completely ejected and was about 20 meters away. So, of course, the whole team sitting there being like, gosh, what happened? We kind of understand a bit of the root cause. Our vision navigation couldn't handle this type of terrain. Again, we were designed to fly 5 times, right? Here we are in our 72nd flight in completely undesigned for terrain. So, I'm super happy with what we accomplished. So again, we had a whole crash investigation, first aerial crash investigation on another planet, rock first. Sadly, we couldn't confirm the cause, 100%. We don't have a black box like we do on all of our airliners here. But it's, most likely we believe that a hard landing caused shock through the legs to travel up into the rotor structure, and basically the vibration shock loading caused all 4 rotor tips to snap off at about 1/3 of the core. So, basically all about here, all the end was broken off. And then basically, these rotors spin at 2,700 RPMs. So, way faster than even like a drone here on Earth, way faster than a helicopter on Earth. And so these things are booking it. And so the second that this rotor system was imbalanced, right? Think about a car that's not properly balanced. You see it all go up down the highway. Well, that's basically what happened, and the hub bearing could not, hold that type of load. And so one of the rotors broke at the stem, and that's the one that got ejected. So, I'm one to say that I think crash is a little bit too strong of a word. But, teach their own. We are grounded, I will give you that. We are a bit damaged. I'll give you that, but we are still powered, we are upright, we are still fully functional, all of our avionics are working. And so I'll just say that, Ingenuity continues to record engineering data, take pictures every day on Mars. Right, we're once again here in a great sandy region. There's a lot of interest in, again, the alien motion of the sand, so we're taking those photos. We're hopefully in an area that's going to keep feeding our solar rays again. So, there's some, crazy hopes that when the rover returns in 5 years, we're still operating, and, we can get all of that data down off of it. But, admittedly, we haven't talked to a helicopter since December. Basically, the rover, left Jethro crater. It climbed the crater rim, and it is, it's left the building, if you will. And so we no longer have good line of sight communication, and so don't communicate with it any longer. But, a bit of a show in your helicopter. Is it alive? Is it not alive? You know, it's going to be a long time before we know. But you know, I just want to leave you on perhaps a helper note. Part of the work I'm doing now is some of the work that we're trying to get proposed. So this is pre-project. This is not been funded by NASA. But we are hoping that in the future, instead of a rover, we are going to send a helicopter. So instead of a coaxial 2-rotor system, we're going to have 6 rotors. Each rotor having like 5 or 6 blades. Ingenuity as a whole, this entire thing weighed about 4 pounds, right? So imagine, this model weighs like 15. It's pretty unbelievable how light this thing weighed. With Chopper, this heavy lift helicopter, the goal is to try and carry a payload of about 5 kilograms, which would be a lot of really interesting science. And the goal is to fly about 3 kilometers per flight. We can go up steep terrain. The goal is really trying to get to terrain that the geologists have always been curious about. One of the missions we're trying to look at is trying to go to the Grand Canyon equivalent on Mars. And what can we do if we can fly up the side and really just look at millions or billions of years in the rock history. The geologists are super excited for that concept. So trying to see what can happen there. So yeah, I think that brings us here to the end. So thank you so much all for attending. I do have some personal recommendations here at the bottom. Of course, there's a lot of wonderful things on the official NASA website. Posters, images, mission blogs. A lot of us, engineers and scientists, we kept an active mission blog, so you can go and read about the in-flight system identification, campaign, or a lot of other things that we try to do. Our NASA YouTube JPL is excellent. I've actually given another talk that's, you can try and find it on there. I personally enjoy watching the Mars guy. He's part of the team that runs the camera on the rover. And he basically just keeps up to date with everything happening on Mars, whether both rovers, Ingenuity was operating. Really kind of fun this year, kind of local news source for Mars. So that's what we're into. So, I'll just say so much more. It's really awesome to be part of NASA, to be part of a program that's just so well loved by everyone. So many citizen scientists have stepped in to, write about our journey. People have emailed me asking for some of our data, being like, hey, can we look at this? And sure, let's do it all. So, really appreciate everyone's interest, and thank you all for coming.
Mr. President, so you'll be heard by the folks at home.
How do you pick the names for features on Mars?
Yeah, great question. There's actually a whole grid system for it. So they've actually put this 1 kilometer by 1 kilometer grid on the surface of Mars. And basically different national parks around the world, not just the United States, get termed that. And so, let's just use Yosemite for example, right? 1 square kilometer will be Yosemite. And so literally, if they find a rock or a hill or anything in that 1 square kilometer that they want to name, they go to the list of names in Yosemite and go, oh, we're going to call that Mirror Lake and Half Dome and that. And so you basically go through regions like Santa, that's a national park I believe in France. So all the names are just these really long French names, and you're like, oh, great. But it keeps interesting.
Question? Give me a second. I'll get Allie over here. She's young. She can run around.
Okay, Martin. You said one of the challenges is the errors that happen as you fly along. What's the biggest source of errors, and what did you guys do to try to compensate for it? Errors? Yeah, in navigation. Errors in navigation.
Yeah, great question. So originally when we were on Mars, we assumed that Mars was flat in our algorithm. And so whenever you kind of deviated from it being flat, you had problems. Obviously, as we went into the Delta region, all that terrain, you're like, okay, that's not flyable. So that's when we had one of those flight software patches. But basically, the flight software patch allowed a digital elevation map where the DEM of Mars to be loaded in to kind of have that be the surface. And so what you ended up finding is the kind of largest deviations between the truth and what that model says it was would then kind of lead to the most error. And in particular, we found that, you know, this DEM is generated by a lot of flat surfaces. And we found in particular that like curved surfaces, like flying over this like rounded hill, kind of caused you some issues. But just as an explanation briefly, the kind of the reason why this is a problem is that if you think Mars is flat and you fly over Mars that's, let's say, slanted sideways to you, as you fly over, you know, things on the left side of your image are further away than the things on the right side of the image. And so it appears like they move slower. And so if you think that everything's actually flat and things on the left side are moving slower than things on the right side, well, that means you're turning, right? And so you basically get slope error, just causes the whole thing to turn without really even knowing it.
Dr. Cacan, I was wondering, you mentioned that the Ingenuity helicopter possessed certain weather prediction modeling and so forth. However, I realize that especially because of the time delay between Earth and the Martian relay systems, that there are inevitably going to be incongruencies, margin of uncertainties, or just unpredictabilities of the Martian weather. So I was really wondering, how was the Ingenuity avoid being buried in sand or covered by dust or being knocked over by wind, I mean, so not even 2 kilograms, or being buried in dust storms or affected by all that? How was it able to avoid all that over almost 700 sols?
Great question. First of all, I'll say that, yeah, it's really hard to get blown over. You know, I love The Martian as a movie and as a book, but the only thing that's bad about it is like the beginning where they think that the whole thing will get blown over by a dust storm. I mean, we're talking about like the 1% Earth's atmosphere. Like, you know, you could have 100-mile-an-hour wind blowing at you, and it would just like feel like a light breeze on Earth, right? Like we have to spin these blades at 2,700 RPM to get them moving. You know, so wind itself is not too big of an issue. You know, from a tipping over perspective, it can be once we're in the air. The biggest concern that we have, for sure, yeah, is dust, right? So there was one period of the mission where, you know, we were about to fly and we got a phone call from the atmospherics team and they said, there's a dust storm on Mars. You know, it's like, okay, you know, cancel the flight. So we don't have a lot of good wind sensors on Mars, but when the winds blow hard enough, the whole surface of Mars gets covered in dust. And so, you know, it's not exactly a wind sensor, but again, you see a lot of dust when there's a lot of wind. And so, just, you know, our orbiters kind of give us a lot of information on that. And then it's a lot of modeling, right? It's a lot of atmospheric scientists have gone through and tried to make these predictions. And so it's a combination of using any measurement we have. The Mars 2020 rover, for a while, had a density sensor on it, had a wind sensor. It has now since stopped working. You know, but that gave us real-time data from the surface of Mars. Oftentimes you had to kind of, you know, plan in advance, and then it was one of those things where, you know, kind of the day of, you get a confirmation and you say, you know, yeah, you know, we're good to fly. You know, otherwise maybe it comes outside your bounds and you say, no, scrap the flight. You know, we gotta redo this. You know, given changes to the environment.
I see. But even then, how did its solar panels not meet the opportunity the rover faced?
I mean, our solar array became less efficient over time, right? So yeah, basically, if you call our array 100% efficient when we landed, we were down to about 60% power efficiency by the time the mission ended. So it was, you know, we basically lost about half of the area of our array to dust coverage, which was why it was actually really cool when we got through that solar cleaning event, and you know, everyone was like thrilled. We got 5% state of charge, charge back. So it was exciting.
Okay, thank you, sir.
Right back here. Right here.
I'll be back. I got a couple stupid questions myself. I always do. Okay, what's on your mind, young fellow?
I was just wondering, given all that you've said, there's a slight amount of hydrogen on Mars. I'm assuming there's some gravity. I'm still having trouble understanding how when you think can fly on Mars.
I agree, you know, and that's why it goes back to that first video I showed, you know, we really tried to prove it was possible. But just as a reference point, right, like 1% of Earth's atmosphere is about the equivalent of 100,000 feet here on Earth. So, you know, yeah, imagine trying to fly a helicopter here at 100,000 feet. You know, we don't even fly on those spy planes right at that high. So, yeah, it's challenging. Again, one of the main design limitations of this whole vehicle is making sure that, you know, again, as this rotates, the tip is moving the fastest, right, furthest away from the center. We have to make sure that the tip velocity stays below Mach 1 on Mars, right? So basically the second that you hit Mach 1, if anyone knows anything about aerodynamics, your drag just skyrockets. And so basically, you know, yeah, the fastest that we can spin these rotors is, you know, we literally take it right up against the, you know, the physical aerodynamic limit, and that's how you do it. You literally, you know, squish all the mass out of the system. You know, we are bare bone system here, and that's really what it takes to fly.
Okay, there was a lady up here that had a question. Let me go. Hang on, let me give you your microphone so we can hear you. Most exercise I got this week.
Okay, 2 questions. First of all, approximately what was the length of your daily trips? Or just so we get some, it was hard to tell from your map.
Yeah, let's say like 400 to 600 meters.
Okay.
So, you know, 1,200, 1,500 feet. That's what, like a quarter of a mile, a little bit less.
Right, the other question is, you're talking about, you originally thought it was flat. What kinds of elevations are you in fact talking about?
Yeah, you know, when it started, it was flat. So we're talking, you know, 1 meter of height difference over your whole area. And then when we reached Santa, we were then looking at like 5 meters of height variation over a flight. And then we got to the Delta region and we were looking at like 15 to 20 meter hills that to deal with. Which again, when you're on Earth, you're like, oh, a 20 meter hill is what, 70 feet, you're like, I can go up a 70 foot hill. You know, but everything is challenging on Mars.
Thank you.
Somebody in the back? We'll go on our way with you.
We've got a couple of control engineering questions. Is that design inherently stable, or is it inherently unstable and is controlled by software? That's the first one. The second one is, what's the dimensionality of the problem? How many inputs and outputs are you controlling?
All great questions. Helicopters are naturally unstable. So there's not a helicopter I've seen yet that is stable, except for those like really cool, you know, like leaves, the acorn leaves that spiral down. You know what I mean? Like, that's pretty stable. But no, like man-made helicopter is stable. So yeah, all require control inputs to stay aloft. There's several main control inputs. You basically have cyclic control and collective control. Cyclic control basically allows you to turn sideways or tilt sideways front back, and collective allows you to go up and down. You have that for both sets of rotors. So you have 2 sets of collectives, 2 sets of cyclic. So you have still cyclic is actually 2, you have like a sine and a cosine. So there's actually 6 control inputs primarily. 4 cyclics and 2 collectives.
Here we go. Okay. Hang on, I'll be back to you guys. We're gonna run. Mayor had to step out for a campaign speech. We were gonna let him give it here, but too many questions about State Street downtown. What do you ask?
Hi, I had a few questions. My first question was, do you believe there was life on Mars during the Milwaukee period? Give a statistic of how it's permanently so, or doubt.
This is all personal opinion. I'm not sure about the specific age, but I think there was most likely life on Mars. I think there's just so much evidence that there's been water on Mars that wasn't there the whole time, but there were definitely long periods of Martian history that we believe was covered in water. So, all the signs are there, we have the heat, we have the water, every ingredient to life we need, so.
You have a follow-up?
Yeah.
Yeah, so I had a few other questions also. One of my other questions was, do you believe humans will colonize Mars, and do you believe humans should colonize Mars? And if you believe we will, what's your estimated time span?
Great question. I think, are you an Elon believer or are you not? So, but no, personally, space is hard. Mars is a terrible place to live, I hate to say it, right? And so as much as I think it would be super fun to colonize Mars, and I think there's, value in colonizing Mars and there's value in colonizing the moon, do I think it's gonna happen, kind of in our timeline, kind of stretching it in my opinion? Earth would really, 500 years down the road level of climate change before we're starting to think that Mars might be a nice place to live, right? We're talking, toxic, no atmosphere, it's just incredibly harsh. Are there values to it? Sure, right? But I think, we don't understand medicine in low gravity very well, right? Every time astronauts on ISS have issues, they mostly come down to Earth. There's definitely some medicine that happens. But again, those people are there for, a year maximum? What's it gonna be like, living permanently in these low gravity environments? What it's gonna be like to give birth in these low gravity environments, right? I think there's a lot of questions that we don't have answers to. It's not just about getting a rocket that can get us there, right? I think there's just a whole other part of the picture that has to get solved, and I haven't seen a lot of that work done yet.
Okay, back here.
Thank you for the talk. I have a question about you working with 200 other engineers and just how managing programs happens that way. I work with 20 other ones and I'm more equal on their hair out. So if you can tell us about how teams are separated and how plans are made.
Yeah, compartmentalization is for sure big. The rover has 11 instruments on it, and we were one of them. Technically we weren't on it, and we arrived on it. But it's a lot of compartmentalization of different tasks, and it's really strong leadership, I think, to get everyone onto the same goal, driven to the same target, and then you basically can get yourself a machine that just works fluidly because everyone is just very clear on what we're trying to achieve.
Next.
Two questions. The first one is, how would you balance the benefits of safety that you get with altitude and of course the cost of flying higher and higher risks of a larger descent? And then the second one is, can you talk a little more about how you locate sites that were safe for landing in environments that is, say, very rocky autonomously?
Sure. So, answer your first question first. The second question first. The video I kind of showed you a little bit of the insight, but basically, as we fly over the surface of Mars, we're constantly looking in the images to try and find safe places to land. So, again, it uses a pretty simple algorithm. Everything on Ingenuity we try to do as simple as possible. And so in this case, we looked at, that whole feature list that you guys saw. And you basically say, okay, well, features are rocks. We want to land where there's no features. And so our hazard detection algorithm is basically just a contrast avoiding algorithm, right? Where it basically just tries to find an area of minimal contrast, which ends up being these sand ripples a lot. And it goes and finds those and then lands there. What was the first question now?
Altitude, relative altitude.
Oh, yeah. So, basically to fly faster, which we really wanted to do, we needed to fly higher, right? So if you think about when you're in a jet airplane flying at 500 miles an hour looking down at the ground, it doesn't seem like that house is going 500 miles an hour. It's kind of going by all nice and gently below you, but if you were in a car going 500 miles past that house, zoom. And so the same thing's kind of true, right? The further above you are, the slower the features in your camera move. And so basically we kind of had a limit to how fast we wanted our features to move. And so to fly faster forward, we had to fly higher. So that kind of gave us the motivation. How we kind of managed it from a risk perspective was trying to do everything incrementally, right? A lot of the times when we flew up to a new high altitude, we weren't flying forward, we were just going purely up. And that just helped simplify things a little bit. So there were a number of flights where, let's say we cruised at 12 meters altitude, got to our destination, we had a little bit of power left, and we're like, okay, great, let's do a pop up to 18 meters, and then we landed. And then when we go on our other flights, we went to 20 meters, that multi-altitude pop up went to 24 meters. So, everything we try and do is just incremental, try and, look at the data of the previous flight, everything still looked good, are you ready to proceed? And yeah, so it's just, trying to bite off as little as you can every attempt. And again, for the System ID campaign, that really kind of gave us our target for where we want to get to. And so again, we just kind of morselled it out.
Thank you. Question? Let me give you the mic.
I have two very unimportant questions, sir. I was wondering what software did you use and how much in maybe megabytes of data did you transfer and receive from the Ingenuity copter?
Great question. We were running Linux on a Snapdragon, I think 805 processor. It came out with like a Galaxy S3 or S5, something like that. So yeah, Linux. We really wanted to say we were the first system on Mars to run Linux, but we were second. Sadly, there was another piece of equipment on the rover that also ran Linux that got turned on before we did. So, but yeah, how many megabytes do we get down? That's a great question. I would probably put it at total guess 3 gigabytes. And honestly, it's probably less. I mean, most of those are images, right? And we take about 200 navcam images per flight, maybe about 8 color images, and then past that, it's just a lot of text logs. So, and maybe even just 1 gigabyte, I'm not totally sure.
Question here.
You mentioned the Snapdragon processor. Doesn't any electronics need to be radiation hardened?
Yeah, and it turns out that's really expensive. What we mostly did was we just took commercial off-the-shelf parts for the processor. The processor was a little bit special. We did have a separate research task that kind of grew into this. We basically worked with Qualcomm to try and rad harden their processors. Basically, one of the things we found is you just turn down the clock speed a little bit, and you just allow a little bit more margins. In this transistor, it's just like ones and zeros. And if you just kind of allow a little bit more time for it to settle on the 1 and settle on the 0 by slowing the whole system down, you actually got a lot of the radiation proofing you need. For everything else, though, we literally just batch tested. We bought 1,000, and we were like, oh, this one, this is the one, buy this one. It was a lot cheaper.
Question from your Vice President. Forgive me if you covered this in your talk, Martin, but were you holed up in a little room in JPL with a joystick? Maybe with a bunch of Atari games, or?
That would have been nice. Actually, we did most of our operations during COVID when no one was in any room, and I operated this from, my kitchen, my parents' living rooms, NASA was great. Actually, when NASA went fully remote due to COVID, there's a lot of people, again, who send commands directly to another planet, and we literally had a legitimate JPL meeting that talked about how to prevent cats from commanding spacecrafts. It's the space bar, you just crash the helicopter. So important times, the cats don't go outside. There were some tough things that people working in the house.
Mr. President, and behind the cartoons on our weekly blog.
Do you know of any plans to put helicopters on any other planets?
So there's the Dragonfly mission, which is led by APL, and they're trying to go to, Titan, I believe, right? So they actually have a very different problem. They're going in, Titan has also about a third of the gravity as Mars, but its actually atmospheric density is much higher. So it's a little bit weird. It's not really like flying, and it's not really like swimming. It's somewhere in between. So they have some of their own sets of challenges. There's several other projects like Chopper that we're trying to propose to work with human space exploration type stuff. There's a lot of kind of advanced scouting missions. We're even trying to put one of these on the moon, right? And you're telling me, okay, there's no atmosphere on the moon. How are you going to spin your blades? Like, sure. We can put little thrusters on them. We're also talking about these things are actually pretty cheap. One of the ideas we floated was like Canon launching them, and just like, oh, we'll just send it that way. It's the moon. It'll float for a while. It'll take all these photos, do all these things, send it all back, and then crash somewhere, and just send another one that way. So we're the whole kind of COTS approach, commercial off the shelf, building these parts, building the system of ingenuity. We're really trying to leverage to see how can we keep using that? How can we kind of use now this cheap platform to do more.
I got one sit over here in the middle.
My wife said, oh no.
You mentioned it was flying and you had a little more power left, so you went up. Could you tell us a little more as how is the helicopter powered?
Yeah, so here we have the solar array sitting on top. Yeah, so this is our solar panel. This is nothing like a solar panel you find on Earth. This panel has been specifically tuned for the type of light you get on Mars, the exact frequency, and so this is designed to pick up most out of that frequency range. So that gives us how we get our power in. We then basically have 4 cell batteries inside this little box here where we store that energy. And most use it to stay warm, but also use it to fly around.
You demonstrated on the Mattel version for Christmas, all the kids are going to want to be buying.
Yeah, here goes. It's this just top component here.
Did you know Julian Knott, the late hot air balloon expert, or know of him?
No.
I think he was in the club, wasn't he? He spoke to us, and Benson was talking to him about so many hot air balloons were of Jupiter.
Venus.
Venus.
Yeah, we want to send balloons to Venus for sure.
They wouldn't work on Mars.
Yeah, not enough density to float in.
Well, I was going to ask you a question about why you don't do 3 or 4 little dinky round, propellers like today's modern drones, and then you showed your next thing is that.
Yeah. But for this size, this is actually the most mass efficient way you can get this much lift out of this much mass. If you want to go up to that a quadcopter configuration, you can, and obviously again we're trying to, but to kind of make it small, this coaxial configuration is the best.
Your radio directions go to the rover, and the rover goes to the Ingenuity, right?
Or yeah, so like communications, go from here on Earth, goes to the Deep Space Network, basically sends the signal out to an orbiter going around Mars. From the orbiter, it goes down to the rover, and then from the rover, we get to the Ingenuity. And then to get data back off of it, you have to go back up that chain.
Got a little time left. Better be out of here by 10. Oh, your mom doesn't you
by 10.
Finally. So, what about the next mission? What is the goal and what's going on? There were going to be 2 helicopters, now there's only 1.
Hard to speculate. I don't know. We should all call our congressman and ask. There's a lot of desirements that we have, a lot of goals that we're trying to propose. But as of now, there is nothing officially scheduled. So, again, we have a lot of proposals out, but yeah, currently do not have an execution.
What kind of kid was he?
Stubborn. So what was the original plan?
Okay, I mean, yeah, so there's been a new number of evolutions of where we're trying to go next. So one of them was the sample return helicopter. Basically, the next Mars mission is going to try and go collect all these rock samples that the current rover is generating. And so at one point they're like, oh, well, we have to go pick up all these samples and bring them back to this new base station for the next mission. And the original plan was to be a rover, and so then we were like, hey guys, we like just proved you could do this in the air. And so then we got on board that mission. NASA overcut that because of just budget costs with the whole Mars sample return mission. And so we've been just trying to reframe it again. There's concepts that we're trying to propose that keep small Ingenuity-like vehicles all the way to that large chopper, right? And they span a wide gamut of goals, but all of them either align with science interests or human space exploration.
Maybe one or two more.
The color that I see in the picture on the left appears very real. Is it?
It has been color corrected. Yeah, the camera that we have on Mars doesn't take true to light photos, and so you do have to do some color correction to try and get them to look Mars realistic.
Do you know what the actual color would be if you were looking at that same thing and while you were standing next to it on Mars?
Yeah, it would look very similar, like a reddish brown. Yeah.
It's got not blue on Mars. It's that color, like the days we have here in June blue.
Yeah, that is true actually. The sky is not blue on Mars. The sky is pretty red.
What is red?
Reddish.
I haven't seen that. One more for the road, Mike. Did you have one?
Yeah, right. Over here.
Okay. This lady up here is going to close this out.
Can I get a rock? A rock?
Yeah, I would love to get a rock from Mars. I don't know. Maybe the best I could do is get one named after you, Paula. I don't know.
Don't you think one might go up there?
If you can fund us to send you a rock, we'll do it. So.
Somebody wants to shout out one real fast while I'm getting President up here with me to close the meeting.
How did you avoid your own shadow in the navigations?
Great question. We thought about several different approaches, including trying to mask out the part of the image where the shadow was going to be, but pretty difficult to prepare a separate image mask for everything's light, stuff like that. It turns out we didn't. We just left it be in there. What happens is we reject features that don't follow expectation, right? So in the first frame, you kind of look at everything, but in the second frame, you move forward, and so everything you kind of saw will get moved back. Except your shadow kind of moved with you. And so those features didn't behave like all the other features. Especially if you go a little bit further forward, you go, those aren't real features, you throw them out.
Martin Cacan.
So because the atmosphere is different, the what gets absorbed by the atmosphere and what makes it down to the ground is just different than what we got here.
Listen, our next meeting in here, will actually be down below, is on August 2nd with Dr. Kate from UC Riverside. But glad to have you join, especially if you've got secretarial experience or maybe treasurer. Tell your friends, and please come back, and I'm going to give this man our official ceramic cup.
All right. This is definitely something.
Okay, thank you everybody for coming. Good night.
But yeah, the next week, I'll move here to the center of the stage. If people want to take a photo with it,